we've studied approximations for these areas. So we looked at Riemann sums left, Riemann sums right, Riemann sums middle, and trapezoids. The trapezoids for the same number of shapes are more accurate than the rectangles, but in all cases, those are approximations. And what we really want is no error. We want exact area. We don't want there to be any doubt. We don't want there to be any confusion. We don't want there to be any offage. We want the exact area. And we've talked a little bit and done a small bit with Riemann sums. And we've really only theoretically talked about. And given our constraints this year, that's about all we're going to do. When we're looking at 4 rectangles or trapezoids, that is less accurate than 10 or 100 or 50 or 1,050 or 50 million rectangles or trapezoids. 50 million rectangles or trapezoids is going to be more accurate than 50 rectangles or trapezoids. We can think about it graphically, how the amount of area that you're over is going to be really small. You could think about it, or the area that you're a little bit too much, the gaps, it's going to be very small because of how small those rectangles are. And when we start talking about 50 million rectangles, we start thinking about how difficult it would be. So we'd have to take a subinterval from 0 to 1, divided into 50 million pieces, evaluate the function 50 million times at the left, right, or midpoint, or using a trapezoid, 50 million of those. And that's if we use a uniform base. If we don't use a uniform base, we're going to have to do a separate base calculation each time. So that's really why we want a uniform base, because we're talking about not 50 million, not even 50 bajillion googolplex, but infinity, which is even larger than any number I've named so far. And it's just impossible to do that many rectangular calculations. So that's why we use a uniform base to expedite those calculations. Now, some of you are probably like, oh, I'll just use a computer. Okay, fine. But this hasn't really been possible up until the most recent vintage of humanity to even have this conversation. And this theory has existed for several hundred years. And it's based on the idea that we have the true area, or as close to true area, as we add more shapes. So we want the exact area, and that's what we're going to talk about. Whether you do a left, right, or midpoint Riemann sum, your area calculations all look like this. And I'll pause here for questions and also to give you some writing time, because there's a whole bunch of junk to write there. It doesn't matter how many rectangles you're doing. You're always going to have a base and a height. So the base is going to be along the axis, x-axis or y-axis. Yes, we can do this for the y-axis, even though we haven't yet. Don't worry, that's coming. It's always going to be a base times a height, 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 base times of height, for as many times as we need to. So did everybody see the dot, dot, dot here? Dot, dot, dot means continue like so. So that means the next one would be b sub 5 times h sub 5. And then after that would be b sub 6 times h sub 6. And you continue like so until you get to b subscript n minus 1 times h subscript n minus 1 plus b subscript n times h subscript n. What's going on here? Well, this is a little bit of new notation that's used when we talk about infinite terms or many terms. And n means the nth term, and in this case, it means the last term we're talking about. So let's say we were only going to 8. That would be b sub 8 times h sub 8. So b subscript 8 times h subscript 8. The term previous to that would be b subscript 7 times h subscript 7, right? 7 is right before 8. Well, that's what the n minus 1s indicate, because 8 minus 1 in both cases is 7. So this is common notation when you're talking about counting a large number of things. We have the last thing, the nth thing, and the next to last thing, the n minus 1th thing. When we get to the third half of calculus, we'll be doing that kind of thing a fair bit, because the third half of calculus is all about infinite sums. Ooh, exciting. Okay. Now, we're doing uniform bases, and heights are going to be points on the function. So because we're doing uniform bases, we're going to factor out that same base number, and then we're going to add up all of the function values. So instead of saying height sub 1, height sub 2, height sub 3, up until height sub n minus 1, height sub n, we're talking about for the first height, left, right, or midpoint, whatever that x value is, goes into the function. The second x value, left, right, or midpoint, goes into the function. Third x value, left, right, or midpoint, goes into the function. And we keep doing that and doing that and doing that until we reach the nth or last term. And again, n minus 1 subscript means next to last. So if we were going out 75 terms, this would be x sub 75, the x value on the 75th subinterval. And this would be 74, literally 75 minus 1. So we keep doing that and doing that and doing that. And we want no error. We want exact area. That means we got to do all of the rectangles. How do we express all of the rectangles? We express all of the rectangles like this. So there's a whole bunch of notation. I'm going to have you copy it down. I am going to pause here, see if we've got questions. So we got all that written down, and this is why math textbooks are not really written for math students. They're written for people that know math already, because they drop all kinds of just stuff on you that you've seen some version of before, or it just doesn't make a whole lot of sense. So let's try to make sense of all that stuff we've written down. And making sense does not mean reading. Reading just means you can decode the word. You don't actually know what the word is. Like you might be able to read the word uniform, but you may not know what uniform means. Like you may think uniform means I have to wear a school uniform, or my work requires me to wear a uniform. No, uniform in this case means equal. So that's what I mean by making sure we're not just reading and decoding. Make sure we're reading with comprehension. So we started here. So I have B, and the B again comes from factoring out that uniform or equal base. So I said B is multiplying, or the same B is multiplying all of these. I slurp that sucker out, and then I've just got a sum of all of the heights. So I've written that using sigma notation. So capital sigma here, and then we have our index I equals 1 all the way up to n. N would be however many of the things we're doing. So n could be 10 or 1,000 or infinity. More on that down here. And what we're doing is we're going to say, okay, when I equals 1, I have x sub 1. That means the first x value on the interval. And then when I equals 2, the second x value gets substituted in the function. When I equals 3, the third x value gets substituted in the function. And then add all of those up for however many n rectangles, trapezoids, whatever it is you're doing. Here, all I did was change the order. And the reason why I changed the order is because it makes the notation we're going to get to a little bit more comprehensible. So we want zero error. We want perfect area. How do we do that? We do every single shape. How do we do every single shape? We do all of the shapes, in all infinitely many of those shapes. So we have rectangles with infinitely small thickness base. Think about how tiny the overridges are. Think about how tiny the underridges are. That's a word I made up. I don't believe that's a word. They're infinitesimally small. And what are we doing? We're adding up all of those heights. How many? Infinitely many. And the base is the same number. It's from the starting x value, like if we're going from 1 to 8, it would be 7 units because 8 minus 1 is 7, right? And we divide that into n equal pieces. N represents how many shapes there are. So again, to use my example, if we're going from 8 to 1, the length is 7. If we divide that into 7 pieces, each one of those bases is 1. If we divide it into 14 pieces, each one of those bases is a half. If we divide it into 21 pieces, each one of those bases is a third of a unit. And because we don't want to write this notation here, we have created a brand new notation to describe this right here. So this is the limit of a Riemann sum, and that is right here. And this notation comes from, it's got two parts to it. It's got what you could think of as the heights, so that's this first part. This kind of elongated S, yes, that's literally where it comes from. S as in sum. We have A on the bottom, B on the top. A is the starting X value. So in the example I was just making up, 1. B, 8. So from 1 to 8. And then dx, this is the base length. The base, again, is infinitesimally small. So it doesn't change anything whatsoever. So what we're doing here is we're using that power of limits we explored in the first half of the class when we talked about the derivative to skirt around those issues of dividing by 0. Remember, the derivative is the limit definite or has a limit definition, and by getting 2 points infinitely close together, actually making the distance between the 2 points infinitely small, we skirt around the issue of we'd be at the same point and it would be 0 divided by 0. So this is the same kind of idea. The base is infinitesimally small, so we call it dx. So it has no effect on the calculation. And we're going to talk about that calculation in a few different ways. One of those ways is going to be a next year thing. I don't mean next school year, I mean next calendar year, because we're about out of time for this calendar year. We call this thing right here the definite integral. So this notation right here is called the definite integral, and it is the limit of a Riemann sum, or this gobbledygook right there. And the definite integral is what we use mathematically to represent the exact area, the true area, the area without any error in it whatsoever. I'm going to pause here. So our first example here is just an example of looking at the notation. So if the question asks for the area between sine of x and the x-axis from x equals 0 to x equals pi, graphically, this is what we're talking about over here. So I've just got a scratch graph. I've got an x and a y-axis, and I'm only looking at sine of x. It happens to intersect the x-axis at both 0 and pi. If I were to write this as a definite integral, I would do the starting x value 0 to the ending x value pi. Those go on top of that integration symbol. So it doesn't need to be as s-like as my first one. This is actually what most of my integrals look like. Think of it more like an F with a tail on the bottom. Then between the integral symbol and the dx is where you'd write the function you were looking at. And if we're being correct, there would be parentheses here, but I'm going to tell you that most of the world leaves those parentheses off. I typically do also. You'll notice that I write parentheses sometimes when they're not necessary, like for sine of x. Not everybody writes parentheses there, but I do. But for the integral, I definitely tend to leave those off. So those are generally left off. So it would look like that exact thing right there. There just wouldn't be parentheses on it. And this is universally applicable. So this isn't like what we started off looking at area, where we could only find the area of certain shapes. So we had to approximate all the other areas. This is universally applicable. So like if I change and I say, okay, this function f of x, and we're going to do it from 6 to 11, I can write the exact same thing. I'm sorry, from 5 to 4. 4 to 5, excuse me, I can't read. I can do the same exact thing. I can do the definite integral from 4 to 5, use that same equation for f of x, the opposite of x minus 6 quantity squared plus 11 dx, and that represents this shape right here. So it's a parabola with vertex at 611 that opens down, and we take this slice right here. So if you're having a hard time looking at that, I will draw something even less to scale. This is the shape we're talking about. So it's got a horizontal linear base. It's got 2 vertical sides, and then its top is a slice of parabola. This right here is represented by this. So the definite integral can be applied universally, even if the function isn't continuous, but we're not going to worry about that for a while. It has to be continuous on the interval declared here. But again, more on that later. We will spend a great deal of time with stuff like that. But this shape here, we can do this way. This shape here, we can do this way. It works for any shape you can imagine that you've got a function for. Universally applicable. Think about the power of that. No matter what it is, we can represent it by the area. Now, there are several ways of determining this value and this value. And one of those ways, the way that we will use most often, is not going to happen until after the winter break. So I apologize for the large gap between when we do this and when we finish this, but that's just kind of the way things worked out. So something I would like to mention is we can always estimate this area by doing a finite Riemann sum. So if I looked at this and I said, okay, well, I don't know what else to do, I could do a Riemann sum. Now, eventually, we're going to have things that always work, okay? But for right now, if it's not a nice geometric shape, we can still approximate the area. But if it is a nice geometric shape, we're going to be able to do it. Okay. More on that here in this example. So this example says evaluate the definite integral from 0 to 5 of the function f of x. The dx is read with respect to x. Now, this is not the whole problem, and I'm only showing you this much purposefully for 2 reasons. The first reason is, again, you cannot mistake being able to read the symbols with understanding the symbols. So when you read those symbols the same way I do, evaluate the definite integral from 0 to 5 of f of x dx, you need to know what the math is that you're actually going to need to do. And this is why math is both glorious and sucks. It's glorious when it makes sense. So those symbols and words right here expand into this idea. We're going to calculate or determine the exact area formed with the function f of x, the x-axis, and the x values 0 and 5. When you read that notation, those symbols, that's what needs to come out of it, because that is going to be what we need in order to actually complete the problem. So let's find out a little bit more about f of x. Here's what we know about f of x. F of x is this function, f of x equals 6. It's graphed right here. So the area we're interested in goes from x equals 0 to x equals 5. It has the x-axis right here, x equals 0 over here on the left, x equals 5 over here on the right, and f of x on the top. And look at that thing right there. That thing right there is a rectangle with a base of 5 and a height of 6. Yes, it is not to scale, don't care. So the area is 30. So the definite integral from 0 to 5 of f of x dx, so find or calculate the exact area formed by the function f of x, the x-axis, and the x values 0 and 5 has a value of 30. How come? Because this is represented by a rectangle with base 5 and height 6. Again, not drawn to scale. Now, we could, and we're not going to do this for everything, if we connect it back to what we're talking about with Riemann sums, what I did was I just said, okay, let's do 5 rectangles of equal base from 0 to 5. Each one has a base of 1 and a height of 6. So that's going to be this rectangle here, plus this rectangle here, plus this one, plus this one, plus this one. So that's 5 rectangles, each with an area of 6, or factor the 1 out. 5 heights of 6 is still 30, times 1 is 30. So it works both forwards and backwards. Okay, let's try this out for another one. G of x. G of x is going to be from -3 to 3. And it's this picture right here. I will tell you that G of x is a semicircle. So let's make sure we know what all this notation represents. It represents calculating the exact area of this shape. So what is this shape? This shape is a semicircle. How is this shape formed? It's formed from x equals 3 to x equals -3 to x equals 3, g of x, and the x-axis. This is how the dx helps me, and the g of x for that matter. It tells me that it's going to be using the x-axis. So what we're interested in is this thing right here, a semicircle of radius 3. So we go from -3 to 3, so the diameter is 6. We go up 3 units, tells me that it's a semicircle of radius 3. Semicircle has an area formula 1/2 times pi r squared. I chose to write it as 9/2 pi. 9 pi over 2 is fine. There's so many ways to do that. This is the definite integral for this function. And one reason why we care about the definite integral is, well, if we do the same thing we try to do the same thing here that we did here, namely, if I go and make equal length rectangles, notice how those rectangles, if I do a base of 1 again, we've got these issues. So I just drew in where the height would be for these rectangles if I was doing left height rectangles. So I'd have one here and here and here and here and here and here. It's not going to be accurate enough to be the actual area. But if we remember that the definite integral represents the true area, and by the way, this is a semicircle, and I can find the area of a semicircle like this, I'm good to go. Another way this question could be looked at is we actually have the equation, the square root of 9 minus x squared. And you may look at that and you may not think much of that, but as we study you will find that that is quite hard to do with one of our techniques. But that's neither here nor there. Let's move on to a couple more. And this is going to be some stuff I give you a little bit of time to work on and struggle with. So here's a couple of examples. This one right here, this one over here. The directions are a little bit different. For the first one, I want you to find the area, write correct notation. For this one, I'm going to tell you to sketch it first before trying to calculate it. And I'll pause here again for questions. Here we go. Let me drop a whole bunch of knowledge on here. Okay, so first things first, let's check out the triangle, the notation first. The notation should be the definite integral from x equals -4 to x equals 4 of whatever you're calling this function. So if you didn't call this function h of x, that's okay. That's okay. I called it h of x. So this is a triangle with a base of 8 units, a height of 4 units, an area of 16. There's a few things I'd like to mention here because we will build on these later. And by so the first thing with respect to x equals heck match something else I'll point out. We could alternately do 2 times the area, or 2 times the definite integral from -4 to 0 of h of x dx, or 2 times the area from 0 to 4 of whatever the function is with respect to x. And in both cases, get the same area as before. And you may have noticed that I was using the definite integral and area interchangeably. The definite integral and area were being used interchangeably. This is similar to, if you recall, the derivative. The derivative is the slope of the line tangent to a function. We often refer to the slope of the function, and that's synonymous with derivative. So the definite integral for a function is often referred to as the area under the curve, or the area between the function and the x-axis, or just area. So that's vocabulary you're going to want to get used to as we progress. Drawing our attention to the second, we want to sketch and calculate the definite integral from -2 to 0 of the function 2x plus 5 with respect to x. Again, the dx with respect to x means we're doing it for the x-axis. And you may have something like this. So we've got the graph 2x plus 5 from -2 to 0. It's a nice triangle right there. The area is going to be 1/2 times the base 2 times the height 4. Because if you go from 1 to 5, that's 4 units for an area of 4. And if you had that, you would be wrong. Why would you be wrong? Think about why you'd be wrong before I move on. Remember, we want to be active. We want to be captains of our own ship of the line. Why would that be wrong? I drew a geometric shape. It's a triangle. The area of a triangle is 1/2 base times height. Well, the reason why it's wrong is because this shape is not the area between the function and the x-axis from -2 to 0. There's this gap right here where I made the bottom of the shape and where the x-axis is, pictured perhaps a little bit more clearly in my new picture here, which I blew up a little bit. So I've outlined here in a darker color the actual shape that we're talking about. So this shape right here represents the definite integral. So it's got the triangle bit, but it's also got the bit under the triangle. So notice again up here how there's this missing gap. That area is not there. Here I've included that. This is the correct area. So how would you do that correct area? There's a couple of ways that I will look at with you briefly. So one way you could do it is to treat it as a trapezoid. And you call this horizontal length right here 2 units as the base, and then 1 and 5, that's this point and this point, those are the heights. So 1/2 times this gives you 6. You could also calculate it as the triangle 4 plus this rectangular part 2 to get an area of 6. So the definite integral from -2 to 0 of 2x plus 5 forms this shape, which happens to be a geometric shape we can find the area of, and that area is 6. And what we've been doing must feel kind of weird because we talked about how we use this definite integral thing to use it for things that are not regular shapes. And here we are using it for regular shapes. And I know why it feels weird, but what we're trying to build up here is a comprehension, an understanding, a level of comfort that this weird notation right here means find the area. Whatever the means are you're using to find the area, and again, we're going to look at other means, it doesn't matter, you're finding the area. And this is where I'm going to pause again. Okay, so make sure you got all this written down. Pause the recording if you need to. We're going to look at this function f, which is line segments and a semicircle, 4 different ways. The first way is right here. And I need you to get used to doing 2 things. The first thing I need you to do is get used to reading the notation. So this is the definite integral from -4 to 0 of the opposite of f of x dx. And what you need to be doing is you need to be thinking to yourself, okay, what math am I going to be doing here? So the math I'm going to be doing is I'm going to be finding the area formed by the opposite of f of x, the x-axis, and x equals 0, and x equals 4. So if you're wondering, how do I know that this is the x-axis? Because of this right here, the dx tells me. The dx tells me use the x-axis. Now we'll have more to say on that in the future, but for our purposes right now, that's what we're doing. Okay, so I'm going to tell a bit of a long analogy to kind of help you comprehend what's going on here. When I took calculus out for the first time, I was about your age, and each day in calculus was fascinating to me because I remembered all of that tedious, boring, just awfulness that was Algebra 1 and geometry and Algebra 2 and pre-calc and all that other stuff. I was just, why are we doing all this? They're like this, okay, fine, I can do it, but it's the worst thing ever. It makes no sense. It's like a bad history class where it's one fact after another. Just awful, awful, awful bad, miserable. Didn't like it at all. I got to calculus and we started doing things. I'm like, oh, all right, well, I mean, that makes sense. That's what's going on here. So the math I'm referring to here is we are reflecting f across the x-axis. This is a transformation. So if we look at the graph of f from -4 to 0, the graph of f from -4 to 0 looks something like this, right? That's about what it looks like from -4 to 0. We're going to reflect that across the x-axis. So the area we're actually going to find here is this one. So there's a few ways of thinking about what's going on here. One of those ways you could think about it is you could say, We're going to take the opposite of all of the heights. Which again are function values. Okay, like that would make sense. That's an okay way to think about it. Another okay way to think about it is and this is based on the graphical proof, we want opposite area because we are now below the x-axis. Honestly, either of these considerations is going to get you to the correct value. Both of these represent correct analysis. It doesn't matter which way you do it. Okay, so when I look at this, what I think to myself is the area from -4 to -2 of f of x is a quarter of a circle. So it's a quarter of a circle, and the circular area is pi times the radius squared, and the radius is 2. So it's pi. The area, the definite integral from -2 to 0 of the function f of x, that's a triangle, so that's 1/2 base times height. The base goes from x equals -2 to x equals 0. So that's 2 units, and the height is 1. So that's 1. So the area is pi plus 1, but I take the opposite of that area. I'll let you marinate in that while I get the next one here queued up. Okay. So going back to the last one before we move on to the next one real quick, we're looking only at the graph from -4 to 0. And for the graph from -4 to 0, because we're taking the opposite of f of x, we reflect everything across the x-axis, like we learned about in math classes before calculus. And then we find the area. So we could do that by taking the opposite of the function values, the heights, or we could think of it as just, we want the opposite of the actual area. Now, the reason why this works two ways, and this is something we will spend more time on, is because I'm allowed to, for this particular type of transformation, say that that's equal, the opposite of the whole area from -4 to 0. You can't do that for all these transformations. Okay, drawing our attention here to letter B, we want the definite integral from 2 to 6 of the absolute value of f of x dx. So we're going from 2 to 6. So 2 to 6 means I got like this jazz, right? That's 2 to 6. Okay. If you take the absolute value of that function, you get this. So the first part is the same. The second part becomes positive. So I've got the area from 2 to 4 of f of x dx. That is a, what kind of shape is that? Looks like a trapezoid to me. Okay. So 1/2, the parallel sides are 1 and a 2, and they are 1 unit apart. So that's 3/2. When I go from 4 to 6, I have a triangle. That's 1/2 a base of 2, a height of -2. You may be like, what do you mean height of -2? Remember, this is the function value. The function value is down there. So that gives me a triangular area of -2. But because this is absolute value, we take the absolute value of the 3/2 and the -2. Okay, here's the next one. The next one is this transformation. And the last one is this transformation. So what's going on with these? So the definite integral from -2 to 1 of f of x plus 2 dx. The definite integral from 0 to 3 of f of x plus 2 dx. Remember, it's not just enough to read that. You need to comprehend what you're reading. So we want the area formed by f of x plus 2, the x-axis, and x equals -2 to 1. But f of x plus 2 needs some translating, doesn't it? So what does f of x plus 2 mean? It means we shift left 2 units, right? That's what that notation means. How about this one here? What does f of x plus 2 mean there? We shift up 2 units. So what I'm going to suggest when I leave you with these as your practice here is you think about what shifting left is going to have, or what the effect of shifting left is going to have on the graph here, and calculate the area from -2 to 1, and what the effect of shifting up 2 is going to have on the graph here from 0 to 3, and then calculating the area. The main things that you want to be thinking about, again, are what does this notation mean in terms of math I want to do, and what's the connection here? The connection is we're doing some type of transformation. Okay, to finish up the recording, we're going to shift left 2 units. So the function from -2 to 1 looks like this. So we're going to go left 2 units. So this point right here is the point -2, 0. This point right here is 1, 1. If we shift everything left 2 units, -2, 0 is going to be over here at -4, 0. 1, 1 is going to be over here at -1, 1, which presents us with some difficulty because we have to now find the area from, oops, that is drawn incorrectly. Sorry, that should be there and that should be horizontal. That's why that looked so funny. We have to find the area from -2 all the way to +1. So how are we going to do that? Well, +1, if we shift left 2 units, was over here at 3. Oops, you can't see that. So +1 before shifting is here, right? After shifting, +1 is over here. Well, 3 after shifting is over here at +1. So that means we've got that. So we have a triangle No, we do not have a triangle. I apologize. From -2 to 1, the function f of x plus 2 is all rectangle. It's a base of 3 times a height of 1, or 3 units. Which I just realized you can't see, sorry. So rectangle here, we're going from -2 to +1. That's this rectangle. Base is 3, we go from -2 to 1, height is 1 because we go up to 1. Over here, we have to go up 2. So if we look at the function f of x from 0 to 3, that is this. If we go up 3, we have the same thing, but instead of being at 1, it's now at 3. So this is the shape we're interested in. So the area from 0 to 3 of f of x plus 2, almost put the parentheses in the wrong spot, is a rectangle, still with a base of 3, but now the height has been shifted up 2. So it's not 1, it's 3. So that's 9 units. Hope you enjoyed your look at the definite integral integrated with previous math in terms of transformations. Peace.